The heart is a smart organ. It does not blindly pump a fixed amount of blood every time. If it receives less blood, it pumps out less blood. And if it receives more blood, it pumps more blood. This ability of the heart to adjust its output based on venous return is called Frank-Starling mechanism or Frank-Starling law of the heart. In this video, we will understand this relationship between venous return and cardiac output and the mechanism behind it. The discussion is going to be very interesting. We will start with the basics and then gradually dive deeper into the concept. This diving will be in 3 steps. First, we will quickly revise the mechanism of muscle contraction. Then we will understand the length-tension relationship. And finally, the Frank-Starling mechanism of the heart. Let's get started with the relevant points from the mechanism of muscle contraction. This is a muscle. The contractile unit of muscle cells is a sarcomere. It has actin and myosin filaments. These are Z discs where adjacent sarcomeres are connected. For contraction, the myosin heads pull the actin filaments towards the center of the sarcomere. Continuous pulling like this results in a shortening of the sarcomere. Such a shortening in all the sarcomeres combined produces muscle contraction. So this is basically how muscle contracts. The summary from this step is that interaction between myosin and actin plays a key role in muscle contraction. That was the first step. Now let's go to the next step, the length-tension relationship. We just saw how the muscle contracts. Now in this step, we will see how much force a muscle can generate during contraction. This mainly depends on the initial length of the sarcomere. This graph shows the relation between initial length of the muscle and tension, or in simple words, force generated during contraction. As we can see, initially with increasing length, the force increases. Eventually it reaches the maximum point, and then with increasing length, the force decreases. But why and how do all these happen? Let's see. The reason is that at different lengths, the degree of overlap between actin and myosin varies. We will start our discussion with the highest length. At such lengths, the actin filaments are pulled beyond the ends of myosin filaments. So there can be no interaction between actin and myosin and no force can be generated. Now, if we decrease the initial length, the actin gradually starts overlapping with myosin. See, at this point, these many myosin heads can interact with actin, so they can generate some force. With the further decrease in the initial length, the overlapping increases. So, the force also increases. In this way, with the shortening of the length, the overlapping keeps increasing and the force also increases. Eventually, all myosin heads are covered, so the force reaches maximum. At this point, we still have a gap between opposite actin filaments. The maximum force is maintained till we have this gap. But with further shortening, the opposing actin filaments start overlapping. So now, the spatial relationship between actin and myosin starts getting distorted. Because of this, the chances of actin-myosin interaction actually starts decreasing. Or in simple words, less number of myosin heads can interact with actin. So the force also decreases. With further shortening, the force keeps decreasing. Thus, starting from the highest length, with a decrease in the length, the force of contraction initially increases and then decreases. And that is why we get such curve if we plot tension against length. At the shortest length, the opposing actin filaments are overlapping each other and the spatial relationship between actin and myosin is distorted. So less force can be generated. With increasing length, the actin and myosin move towards the optimal position for contraction. So force increases. The length where we see the maximum tension is also called optimal length or L0. With further lengthening, the ends of actin filaments start moving beyond myosin filaments. So force decreases. So this is a length-tension relationship. The take-home message from this step is that the higher the initial length of the muscle, the more is the force of contraction. However, this happens only up to a limit. Beyond that, an increase in length results in a decrease in the force of contraction. So this was the second step in our discussion. Now the third step is the Frank-Starling mechanism of the heart. We saw the length-tension relationship for skeletal muscle in the second step. For the heart, we can draw a similar graph. It's end-diastolic volume against stroke volume. See, the end-diastolic volume is volume of blood in the ventricles at the end of the diastole. The more this volume, the more would be the stretching or lengthening of ventricular musculature. So we can say that end-diastolic volume is equivalent to the initial length of muscle as we saw in this graph. The stroke volume is determined by force of contraction. So it is also related to the tension in this graph. Coming to the curve itself, it is also similar to the one we saw. In this part, with increasing end-diastolic volume, the stroke volume also increases. Eventually, we reach the optimal length where we see the maximum stroke volume. With a further increase in the end-diastolic volume, the stroke volume starts decreasing. However, the good news is that the normal operating point for the heart falls here, where end-diastolic volume is about 120 ml and stroke volume is about 70 ml. So even with changing conditions, the heart operates in this part of the curve, where increasing end-diastolic volume increases stroke volume. Normally the heart does not operate in this range. This curve is called Frank-Starling curve. Now let's talk about the mechanism behind this relationship. The fundamental reason for this type of relationship is the same as we saw in the second step. It's changing degree of overlap between actin and myosin filaments with changing initial length. Along with that, one more factor plays a key role here. That is the side-by-side distance between actin and myosin filaments. See, when a muscle is stretched, its thickness decreases. At molecular level, this results in a decreased distance between actin and myosin filaments. So now the cross-bridge interaction between actin and myosin increases. So the muscle can generate more force. Thus, with increasing stretch, the force of contraction increases. So this is the mechanism of how increasing venous return increases stroke volume. The summary from this step is that increased venous return increases end-diastolic volume, which in turn results in a greater stretching of ventricular musculature. The stretching decreases side-by-side distance between actin and myosin filaments. So cross-bridge interaction increases and more force is generated. The forceful contraction increases stroke volume. In a nutshell, increased venous return increases stroke volume. So this was the final step in our discussion of Frank-Starling mechanism of the heart. Now let's understand its importance. One is that it equalizes output between the right and left sides of the heart so that the distribution of blood in pulmonary and systemic circulation is maintained. For example, if right heart pumps a large volume of blood, more blood enters the pulmonary circulation. So the venous return to the left heart also increases. This results in an increased end-diastolic volume in the left ventricle. So the ventricular musculature is stretched more. Now due to the mechanism that we just discussed, this results in increased force of contraction. So the extra amount is ejected by the left heart also. Thus change in the pumping by one side is balanced by the other side. So in long run, the output of both the ventricles is kept equal. If such equalization does not happen, the blood would shift from one circulation to the other. For example, in the same situation, if the left heart does not increase the output with increasing input, the blood would start accumulating in the lungs. But this does not happen thanks to the Frank-Starling mechanism. The second importance is in situations where more cardiac output is needed. For example, during exercise. In such situations, multiple factors such as sympathetic activation causing vasoconstriction, and increased muscle pump activity increases the venous return. The increased venous return results in increased end-diastolic volume. Due to the increased stretching, the force of contraction is increased and more blood is pumped. This increase in pumping is required during exercise. Please note that this increased pumping is merely due to increased venous return. We are not yet talking about any external influences on the heart. The inbuilt Frank-Starling mechanism of the heart can independently increase the cardiac output in response to such an increase in venous return. It's a different thing that in the case of exercise, this mechanism is also assisted by increased heart rate. So, the Frank-Starling mechanism and increased heart rate, both factors act together and increase cardiac output to meet the demands of exercise. So, this was about the importance of Frank-Starling mechanism of the heart. This covers all the points for the video. Now let's have a quick summary. With the increasing venous return, the end-diastolic volume increases. This results in increased stretching of ventricular musculature. Due to the length-tension relationship, the increased stretching results in an increased force of contraction. So stroke volume is increased. Thus, with increased venous return, the stroke volume increases. The mechanism behind this is that with increased stretching, the overlapping between actin and myosin becomes more optimal, and also the distance between actin and myosin decreases. This increases the cross-bridge interaction, so the force of contraction increases. That's it for this video. You can find notes on this topic and explore our entire animation video library at our website. The links are in description. If you like the video, hit the like button, share and subscribe. Thanks for watching. See you in the next video.